Yo caí redondita y me fui al auditorio.
Ah, y no te encontraste con nadie.
Sí, con Rosario.
Ah,
Caímos
ok.
redonditas, pero ya estamos. Gracias.
El doctor Stephen Koch, que es un profesor adjunto en la Universidad de Arizona. Lo va a presentar David Kenton, quien lo invitó, y bueno, estamos muy contentos de que esté con nosotros el doctor Steve Koch. Thank you very much for coming or for giving this talk, Dr. Koch. Adelante, Steve. Digo, David.
Okay, sí. Bueno, primero doy un breve resumen en español. Y pues Steve va a dar su charla en inglés. Por lo que entiendo, pues entiende un poco de español y hasta habla un poco, y su hija creo que sí lo habla bien. Sí, me explicó. Ok, bueno, voy a dar como un resumen de su carrera, pues larga y bien compleja. Bueno, Steve hizo su licenciatura y maestría en meteorología en la Universidad de Wisconsin, y luego fue a la Universidad de Oklahoma para hacer su doctorado. Él realmente comenzó como investigador en meteorología en el NASA Goddard en Greenbelt, Maryland. Y él pues trabajó varios años en NASA Goddard, y luego fue a la Universidad de, perdón, es que tuve un problema con mi compu. Ok. Él fue a un puesto de profesor en la Universidad de North Carolina State, trabajando con cuestiones de previsión de tiempo, de modelos numéricos. Y luego, después de su tiempo allá, ya empezó a trabajar en la NOAA, como director de varios institutos, incluyendo pues lo más reciente sería el laboratorio de tiempo severo o tormentas severas, eso. Pero también director de varios otros, Earth Systems Lab y otros laboratorios, digamos, de la NOAA. Y trabajó muchos años y directó muchos proyectos para desarrollar cuestiones de radares y de nuevo de previsión de tiempo para el servicio meteorológico. Ha ganado muchos premios, varios premios dentro del Weather Service del Servicio de Meteorológico, aparte de nacional. Últimamente ha estado trabajando como adjunct professor en la Universidad de Arizona y también en Embry-Riddle. Y entonces hoy nos va a dar una charla sobre la naturaleza de convección en tormentas severas, que él ha estudiado básicamente toda su carrera. Y al final, si hay tiempo, va a hablar sobre la campaña que vamos a mandar la propuesta al NSF, creo que en diciembre, si no me falla la memoria. Y si alguien se interesa mucho en pues, esos puestos como director de estos laboratorios y esas cosas, él también puede dar hablar de sus experiencias, los proyectos a súper gran escala que dirigió. Él hasta tiene varias diapositivas sobre ese tema. Entonces, pues eso podría ser después de su presentación. Pero bueno, en fin, pues como digo, él va a dar la charla en inglés. Y pues muchas gracias, Steve. Thank you, Steve, for taking this invitation to present your work to us. So you can go ahead and begin now.
Muchas gracias. Buenas tardes. Es un honor para mí haber sido invitado a presentarles este seminario hoy. And I would like to just say that I'm very honored to have been invited to present the seminar to you all today. So I will, we're getting started here at about 15 minutes after the hour. I'm going to time myself for about 50 minutes, I guess, see how this goes. Yes, so I guess, let me do this here. Okay. So the outline, there are three major topics, science themes. I want to talk about the modes of convection and associated natural hazards. I realize that this audience is diverse. Some of you, this may be very well acquainted with the topic, and for others of you, maybe not, but I presume nothing. And so I will start with the simple and progress to the more complex. I want to emphasize upscale feedback effects of organized mesoscale convective systems. And as associated with that are convectively forced dynamical imbalances resulting in gravity wave and Rossby wave production. If there's time permitting, I'll discuss just very briefly, the North American monsoon and a proposed project called Convect. And following the seminar, if there's anyone interested and still there, I can talk about the accomplishments that I was serving as director of the National Severe Storms Laboratory, but that's not part of the seminar. So I wanted to get right into the convective modes. Everyone should be familiar with the idea of air mass storms, single cells. There's only a single updraft. There's no initiation of subsequent convection in any organized manner except by forcing along the gust front, which is the leading edge of the rain-cooled outflow. So the life cycle of an air mass storm is about 30 minutes, and they form under a variety of conditions of CAPE, that is convective available potential energy. But the common thing is very weak vertical wind shear. So basically in the schematic below, you see how once the precipitation has developed, it falls right into the updraft and kills it. So this is common behavior for single cell storms. I'd like to contrast that with multi-cell storms. You see here a multi-cell complex with 4 cells. And these frequently develop from repeated development of new cells, again generated along the gust front. As in the picture shown here, you can start to see daughter cells or feeder cells sometimes they're called. And if you can see my mouse, you got kind of like a staircase, a behavior of convection that is associated with these kinds of storms. The most severe forms of these storms can persist for hours, produce large hail and damaging straight winds if there's sufficient CAPE. So I like to look at a multi-cell complex like a family. So the newborn cell is on the left. It's the vigorous, hard, boiling, convective cell. It's the newest cell. To its right is a maturing cell, which is beginning to lose that boiling kind of appearance. And then the mature cell, which has a well-defined cirriform anvil, and usually is the stage in which the most precipitation occurs. And then the older cells, where basically the updraft is diminishing, it still does produce precipitation. And there's the grandfather cell. So it's almost like looking at a family tree. Point about all these multicells is they form under conditions of relatively strong vertical wind shear. The value is of the order of 10 to 20 meters per second of vertical wind shear between surface and 6 kilometers above ground. This is what we call moderate shear, 10 to 20 meters per second. So the shear acts to maintain the longevity, the duration of this storm system and allows for this multiple convective growth to occur. In a summary, you have single cells, multicells, and then supercells, which occur under conditions of very strong vertical wind shear. The supercells are those that where the updrafts can be quasi-steady, and by that I mean lasting for 45 minutes or an hour or even longer, and their propagation is governed by vertical pressure gradients that extend over a very deep column of the atmosphere, rather than just by low-level lifting along the gust front. Going back to multicells a second, sometimes it gets a little confusing when we talk about where the daughter cells, the feeder cells, develop. Whether it's up shear or down shear depends on whether the cells are propagating in a continuous fashion or a discrete mode, and what that direction is of the low-level wind shear versus wind rather to the shear. So it gets a little bit more complicated than I've shown it to you. The classical schematic model of a multi-cell system is a squall line, which has a leading convective line, which is shown here. Can you all see my mouse?
Yes.
Gracias. And then to the rear, there's another region called the trailing stratiform region. Associated with the leading convective line is a high-pressure system, a meso-high, produced by cold downdrafts associated with melting and evaporation of hydrometeors. And then behind it is a wake low, which is actually on the backside of the stratiform trailing region. This wake low turns out to be very important as we go to talk about other kinds of convection in just a few minutes here. Associated with that wake low, you see these arrows that indicate flow towards the low pressure. This is the indication of a rear inflow. So the intensity of the wake low depends upon the relative roles of evaporation over other processes in the stratiform region. If you cut a cross section through that squall line, you'll see the air comes in from the right, hits the gust front, which is located here. So this air here is rain-cooled air. And so the air coming in from ahead of it is lifted abruptly and rapidly rises into the top of the cumulonimbus cloud, and then diverges here, produces the anvil. New cells tend to form, as you see this one here is, along the gust front, right? So this is, the low-level shear is from the right to the left in this case. So these are propagating up shear. And as the air continues to rise, hydrometeors are produced, and then there's a combination of microphysical processes, including vapor deposition and coalescence and riming and so forth, that all give rise to the generation of rain or even graupel or hail in this region. This is the downdraft, the cold downdraft. The air then continues rearward, ascending front to rear flow into the trailing stratiform region. Beneath that is a descending rear inflow. This is a dry airstream that enters the back of the upper parts of the cloud and then descends, and this is associated with the wake low. So this is being driven by the pressure gradient force associated with the wake low. The rear inflow jet is, if you look at it dynamically, on the left is a strong rear inflow. The arrow here depicts that rising flow up and over the gust front. You see the blue dome, that's the cold dome, the cold pool. And so this is being forced up and over that. The circulations here, positive and negative, indicate that the air that's forced above the gust front is such that the warm air ascends and the cool air descends. It's thermally direct. So this is what these two cells indicate, counter-rotating vortices. And then that continues to ascend through the cloud. This particular thing on the left is one where there's an 8-degree difference. If you look at a skew-T thermodynamic diagram, this is a condition where the lifted index is -8. It's quite unstable. And for this kind of situation, you get a more intense rear inflow associated with the stronger low pressure. And we'll talk, the reason that this is a low pressure is easily understood by looking at this equation for the perturbation pressure, buoyancy pressure, which says that the pressure perturbation is associated with a negative change of buoyancy with height. So you get a low pressure here because the buoyancy is increasing with height you see in this QT here, the maximum buoyancy is right in here. So the low pressure is going to be located here where the maximum change with buoyancy with height occurs. And once you've got this mesolow created, then depending on the buoyancy, it'll be a strong wake low, or in this case on the right, a weaker one. The stronger one will produce a rear inflow jet or a stronger rear inflow. So let me move ahead to another topic called derechos. These are widespread, long-lived windstorms, thunderstorms that produce a long swath of wind damage. Specifically, Mike Corfidi actually described it in more detail as a family of damaging downburst clusters associated with a forward propagating MCS, mesoscale convective system. And during part of its existence, you'll see either one of the following features: bow echoes, mesoscale vortices, rear inflow jets. The point is that they have to be at least 650 kilometers long in the damage path. So if you look on the left, this is in the state of Missouri, central part of the United States. You see this, looks like the old squall line with the leading convective line and stratiform precipitation behind it. But you see that there's a circulation here, a mesoscale convective vortex right there. So looks like a comma. Associated with that circulation is a very strong rear inflow jet that's coming in from behind and is being swept up into the MCV, the mesoscale vortex. If you look at the Doppler radar radial winds, in fact, you see right here very strong circulation here associated with the head of this bow echo and MCV. This is the characteristic signature of derechos. Here's an example of a progressive derecho, which is affecting the area from Illinois. Here's Lake Michigan, Illinois, and it's heading towards the Middle East. The mid-Atlantic coast. Here's the damage swath, and each blue dot is a severe damaging wind event. And you see most of the hazards are damaging wind, although if you look carefully, you see little yellow squares. These represent damaging hail. And so you see it's at least 650 kilometers in duration. And then you can see here in the upper left how it progresses with time. So as you can see, the hazards can be quite significant: loss of life, loss of power, transportation being affected. Basically, airlines are shut down entirely. Like the Chicago O'Hare Airport would be shut down in a situation like this. So I was the director of National Severe Storms Lab, and you probably want me to say something about tornadoes. I'm not going to say a lot about tornadoes, but tornadoes are generally produced by, for the most part, not entirely, by supercell thunderstorms. These are supercells have this rotating, cyclonically rotating vortex coincident with the updraft, and it's about 5 to 10 kilometers in width. So this is a dramatic indication of a rain-free, rotating updraft of a supercell. The characteristic features of this is the green represents a precipitation region, and it has a characteristic hook echo. Ahead of it is a bounded weak echo region, which is to say there's weak echo bounded to the west and the northeast by higher reflectivity. This indicates the updraft core. The heaviest rain and largest hail are in the dark green, and then the gray represents the upper level clouds. And then you see a little tail down here. This, if you look at it, see the eyeball, if you're looking at this from the east, this will look like this rain-free cloud base, this stair-stepping of cells moving this way. So again, single quasi-steady updraft, the bounded weak echo region, the hook echo, and then the wall cloud is this feature down here. This is where the tornado will be produced. This is the mesocyclone. Its width is 5 to 10 kilometers. And So these are the characteristic features of classic supercells. And then I want to say a word about hail production. The boundary weak ecoregion is very important here. If you look at the reflectivity as a function of height, at the low levels, you see the Hook echo, the boundary weak ecoregion. And then as you go up higher, you begin to see how its weak echo is entirely surrounded by higher reflectivity. And then as you go higher, it eventually closes off and has high reflectivity above that location. So this is a feature that is important for understanding hail development. If you see here on the left is the Hook echo. And if you cut a cross section through this, you can see that there's this bounded weak ecoregion in here in the reflectivity shown in color. And then there's this echo overhang. This overhang is actually, you're looking from A to A prime. So what are we doing? We're looking from southeast to northwest. So what I'm saying is to the southeast of the boundary weak ecoregion is this echo overhang. This is where the embryos, the grapple, are injected into this very strong updraft that's rotating cyclonically and produces this kind of behavior. And then recirculates. So what happens is once the particle grows to such a large size that its terminal velocity exceeds the updraft, it will descend, it will accrete more liquid water onto the ice, onto the grapple, forming hail. It'll rise again, and it'll go through this multiple times. The hailstone here has gone through 1, 2, 3, or 4 cycles up and down through this bounded weak ecoregion. This is the cause of large hailstorms. You need the strong vertical shear. You need this kind of reflectivity structure. So I'll kind of highlight that with little vortices to give you the idea of what I'm talking about here. So you can see the updraft and downdraft. And then on the left, you can see the cyclonic rotation of the mesocyclone. I don't know if this is how this is coming across the internet, but it's supposed to be a movie. And you're seeing an actual cloud with a mesocyclone, and this is the mesocyclone. It's about 5 to 10 kilometers wide. And this little feature here is a tornado that's forming just ahead of that mesocyclone. So it gives you an appreciation of the difference in scale, about a factor of 10, between the size of a tornado and the size of the mesocyclone. I love this animation because you can actually very easily see the strong rotation of the supercell. All right. Tornadoes come in different sizes and strengths and shapes. The strongest being what's called the EF5, extended Fujita scale, with winds in excess of 200 miles per hour, often form a wedge shape. I have personally experienced this kind of tornado before from a pretty short distance away. Basically, everything in its path will be ultimately destroyed like a nuclear bomb. But nothing makes it through something like this. All man-made structures are destroyed, for the most part, except maybe a nuclear facility. But even there would be damage. And as you go down in scale, the size decreases. It gets to be narrower, and the wind speeds decrease. But even here, it wouldn't be safe to drive your car through a rope tornado because the winds are enough to cause your car to overturn. And a mesocyclone may be formed, but it's not essential. All right, now I want to focus. Now that I've given you an appreciation of single cells, multi-cells, supercells, what causes hail, what causes strong damaging winds, the ratios. I want to talk about now larger scale systems and upscale feedback effects. The upscale growth of convection, if you want to develop into a long-lived, large MCS, mesoscale convective system, MCS, what you need is deep layer shear, shown here by this broad arrow, that has a large component parallel to the gust front or cold front, whatever boundary is initiating convection. The shear needs to be parallel to that, because then the individual little cold pools, as you can see here, will merge together to form a very impressive gust front and cold pool and maintain that system. Contrast that with the situation on the right, where the shear is at a large angle relative to the convection initiating boundary. The convective cells, bing, bang, 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 they maintain their discrete behavior. They're discrete, they're not continuous, and they're often very severe. but this is not the kind of situation that promotes long-lived MCSs. So go back to MCS, the Glossary of Meteorology from AMS says it is an ensemble of thunderstorms producing a contiguous precipitation area on the order of 100 kilometers or more in horizontal scale in at least one direction. So here's that picture again of the leading convective line, the transition region, and the trailing stratiform region. You can also see a gust front. This is the leading edge of the cold outflow by that thin line in the radar reflectivity. You might ask yourself, why 100 kilometers? Is this arbitrary? Well, it's not arbitrary. It depends on the dynamics because it's the scale at which the Coriolis acceleration becomes significant, which is v over f, where v is the scale velocity. If you're at 20 degrees latitude, then this scale is larger than 100 kilometers. It's maybe more like 200 kilometers at 20 degrees latitude versus 40 degrees latitude. But it's determined by a v over f. And how it happens is that these large cold pools merge over time, as I described in the previous graph. This is what we mean by upscale growth of convection. Once you've got that happening, interesting things can develop. Like here's again that rear inflow jet with the mesoscale convective vortex, which I highlight there in the top is a cyclonic rotating element, mesoscale convective vortex. I want to be clear that this is not a mesocyclone that defines a supercell. These are smaller scale. I'm talking here about a little bit larger scale that is associated with bow echoes and derechos. If the rear inflow jet and the MCS persist long enough, then the cyclonic bookend vortex becomes stronger than the anticyclonic.
Steve, I think you froze there.
This is in the morning on the 8th of July from infrared and hence infrared satellite imagery. You don't know what's underneath that. You know it's deep convection, but you don't know what character it has. But just a couple hours later, when we look at the visible imagery, lo and behold, there is an MCV, very strongly evident as a rotating vortex. These can last for a day or two or 4 or 7 or 2 weeks or even 4 weeks and go around the entire globe. Lance Bozard has studied these things. Here's an example where there's an incipient mesoscale vortex here in western Nebraska. And then in the afternoon of that day, new convection develops, deep convection. It gets to be severe. It's even better to find the MCV. So these MCVs can go on for days generating convection one day after another. This is an upscale feedback effect. The notion of mesoscale convective complex developed by Bob Maddox, a former director of NSSL, is that these are basically just a subset of MCSs. That they're defined on the basis of satellite imagery. Large, circular, long-lived, very cold cloud shields aloft. And underneath the cloud shield, you can see here, you can have any kind of convective mode, bow echoes, MCVs, small lines. You don't know. The definition doesn't tell you what it is. All the definition says is it's very cold, large, semicircular shield in the infrared satellite imagery. That's all it says. But that is an MCC. And Velasco and Fritsch some time ago looked at in the Western Hemisphere where do MCVs occur, and they found a couple of interesting things. Of course, there's quite a lot of activity in the central United States, but also just north of the equator, Panama, Colombia. This is a region where you're near the intertropical convergence zone and off the west coast of Mexico. So these are actually, some of these you see hurricane symbols indicate that MCCs actually developed into tropical storms. This happened just this past week. This is a fairly common behavior in the eastern subtropical Pacific Ocean. You also see down here in Pedre and so forth that there's quite a region of MCC activity going into Argentina, but it's primarily a little bit northeast of there, but not into the Amazon. So 4 epicenters, central United States, subtropical Eastern Pacific, down near the ITCZ, and in this region east of the Andes Mountains. Now, an area I've been doing research on recently is to look at the upscale feedback effect. One thing that we've discovered is if you look at this for an MCC, the cyclonic vortex here is present at 500 hectopascals, but at 200 hectopascals, it's anticyclonic and divergent. And there is a low pressure associated at 500 millibars and a high pressure at 200 millibars. You say, well, why is that? The reason has to do with the vertical distribution of diabatic heating. So in the case of a classic deep convective, long-lived MCS, this would be a typical profile of convective heating, the maximum occurring around 500 to 400 millibars. Again, looking at that simple equation, you can understand from this that you're going to get a low pressure beneath the level of maximum heating, high pressure above the level of maximum heating. So very simply understood, you're going to get this dipole of high and low pressure associated with deep tropospheric heating. Associated with that is a perturbation of potential vorticity. The dashed lines here are isotopes potential temperature, and you see there's a cool pool, a warm pool, and a cool pool, which you can see reflected in the isotopes. According to the equation for isentropic potential vorticity, it's related to the vertical gradient of static stability. It's related to the vertical gradient of potential temperature, rather. And you see that you're going to get a PV maximum here and a PV minimum aloft. So this is characteristic of deep convection upscale development. A PV max is generated around 500 millibars and a PV minimum at around 200 to 250 millibars. Associated with that is an influence on the wind field. On the left, this is a schematic picture. You see that a jet streak has been developed on the northwest side of this high pressure system at 200 millibars. Okay, and if you look at the total wind field, it looks like this. So what's happening is you're superimposing the MCC anticyclone here with the background synoptic wind field, which is from the southwest. And you get this mesoscale jet streak, or what I've called jetlet, on the left flank of the MCC, in this case, the northwest side, because we have southwesterly flow aloft. One of my students, we published a paper last year. This is Manda Chasteen. She looked at schematically and also very detailed observational analysis, modeling analysis of this kind of effect where you have a baroclinic flow, you have a temperature gradient, and thermal wind applies, how a jet streak is created. And in this depiction at the initial time, you see this representation of deep convection, the divergent outflow aloft. And you see here that this represents a jet streak forming on the northwest side as the outflow impinges upon the height gradient to the northwest side of the convective element. And if you look at the accelerations of winds in terms of the U and V wind component and explain that in terms of the nature of the ageostrophic wind, it makes a lot of sense that you're going to get accelerations here associated with the negative U ageostrophic and positive V ageostrophic. All right. With time, this expands and this jet streak develops and it's an unbalanced jet streak. Associated with this jet streak aloft, a la Uccellini and Johnson in 1979, will be an isalobaric response at low levels, which is the low-level jet, is generated in response to isalobaric, that is, rapid pressure falls underneath the jet streak aloft. Why is there a fall center of pressure? Because this jet streak is divergent aloft. So you're going to have for upward motion and pressure falls down here. We looked at a case. This is not just a normal case. This is the strongest tornado event to ever occurred in recorded history. You see the date of 27th April 2011. There were more than 300 tornadoes in the southeastern United States in this region here. And this is at the beginning of the outbreak of tornadoes. There's a what we call quasi-linear convective system, or essentially a squall line with the trailing component and leading convective line. And associated with this deep convection development, we see a jet streak here in this model simulation. This is a WRF model at 1.5 kilometer resolution. We also see an upstream development jet streak. This is not associated with convection, but this one is. And how do we know that? Because when we ran the model where we did not allow for convective diabatic heating feedbacks to occur in the model dynamical equations, the momentum equations, if we disallowed that, then you don't see this jet streak at all. It just doesn't even appear. Associated with this jet streak is, here it is, big pressure rises aloft at 250 millibars. And they're big. They're 125 meter height rises, okay? And then here is the wind speed difference, over 100 knots. This is an incredible upscale feedback effect. This is not insignificant by any stretch of the imagination. So when we say unbalanced, what do we mean? Well, we use the nonlinear balance equation, and here's another situation coming into California and Arizona. There's a negatively tilted upper level trough, and with that trough, there's a vorticity maximum shown by the bullseye, the geostrophic wind max just to the south of that, of course, and the real jet streak is off here to the east in Northern California. There's an axis of this is the ridge axis and the height field, and this is the trough axis, and this is the inflection axis. So the nonlinear balance equation here, there are four terms, but if you do a scale analysis, it's the first two terms that determine if there is a significant residual in the nonlinear balance equation. And that's the Laplacian of the height field and the Jacobian, which is the tensor here, rather complicated, but it turns out that when you look at the various derivatives, you can calculate that you're going to get rapid changes in a very small distance. As you see here, the yellow is where the Jacobian residual is large, and the blue is where the Laplacian of height term is large. It's these two terms that offset one another that generate a large residual in the nonlinear balance equation. This is where you get the imbalance. And it's near the inflection axis, and we found that as the jet approaches the inflection axis, this is where we get the imbalance. So this was published in multiple papers, one I published with Louis Uccellini years ago, but also one of my PhD students, Fuqing Zhang, and then recently, just last year, in the bulletin of the American Meteorological Society, we wrote a tribute paper to Zhang, who is no longer living. But in this, Fuqing had developed a schematic representation of what happens. At the initial time, you have a jet streak, which is a geostrophic or quasi-geostrophic balance. Here's a stationary front at low levels, okay? And the lines represent the heights at 300 millibars. So you can see that there's an inflection axis in the height field right through there. So here comes the jet. It's geostrophic. It's approaching the inflection axis. According to what I just told you, I'm expecting imbalance to be generated as that jet crosses the inflection axis, because the Jacobian and the Laplacian terms become out of balance with one another. This is exactly where mesoscale gravity waves are generated in this darker purple region here. The jet now is no longer geostrophic. The geostrophic jet is back here with the strongest height gradient, but the actual jet is ahead of it and is crossing over to the other side of the inflection axis. This is what causes the imbalance, people. And when you look at a cross-section through this, associated with this is a train of gravity waves, and these are inertia gravity waves where Coriolis force is significant. And there's a train of them propagating upwards into the stratosphere, another train that propagates down into the troposphere, okay? And there's a lot of vertical energy flux associated with these kinds of waves. And a tropopause fold, a dynamical tropopause, is associated with this development. This is the classic situation for mesoscale gravity waves to be generated. Zhang in 2004 looked at this using a more idealized baroclinic wave model, and he found that, again, here's a jet. As it approaches the axis of inflection, you see the trough and ridge pattern amplify. It develops a negative tilt. northwest to southeast, and the jet approaches the inflection axis, and you can see these gravity waves being generated with a wavelength of 150 kilometers. These are not your kind of gravity waves that you may be thinking about that are associated with inversions. Those maybe have a wavelength of 5 kilometers or a few kilometers. This is 150 kilometers, and they occur as the exit region of the jet approaches the axis of inflection. In a theoretical study by Bayes, he looked at how important the heating depth is to the nature of the gravity waves, and very clearly, if you look at the heating depth from 0 to 15 kilometers, as you go from shallow heating to deep cumulonimbus convection heating, the dominant wave phase speed goes from 10 meters per second to over 40 meters per second. And the wavelength is 175 to 200 kilometers. Now, this is a theoretical analysis, but we've seen this in the observations over and over again. The wavelength and the phase speed are not very sensitive to the horizontal scale of the heating, but they're very sensitive to the vertical depth of the heating. And these gravity waves are very fast, 40 to 50 meters per second and wavelengths of 175 to 200 kilometers. The weather that's associated with this, I can go on to a long story with you, but I've seen lightning storms in rapidly developing snowstorm situations, shutting down airports, where because of grapple and hail and lightning associated with one of these nonlinear gravity waves. I've seen this happen at Logan Airport in Boston, O'Hare Airport in Chicago. These are published papers. There's a lot of interesting weather that can occur with these kinds of inertia gravity waves. And if they are ducted, again, these are transporting energy vertically into the stratosphere. But if you have a wave duct below a level called the critical level, where the wave phase speed equals the wind, then the wave energy is propagating upwards and then gets reflected back down again underneath. This is the wave duct here. And you see the isentropes are all, there's no tilt to them down here. And so this is what we call a ducted wave CISC model. It's ducted below the critical level height. And the idea of the convection is it is the source of energy for the waves. So it's a very interesting paradigm, dynamical paradigm for upscale development. So in summary, synoptic and mesoscale forcing provides the environment and the forcing, that is the lifting, to produce deep convection, as I said at the beginning. If you want a long-lasting MCS or an MCC, then convective diabatic heating will enhance the surface cyclone through an induced circulation that allows the penetration of the potential vorticity anomaly downward. That came from that schematic I showed you of the mesoscale gravity waves, and I showed the dynamical tropopause. It was pointing downward. This is associated with the convective heating as the jet stream plows into the axis of inflection and convection is generated by the gravity waves. The deepening cyclone develops a stronger low-level response in terms of a low-level jet being generated. This is the isobaric forcing, local pressure tendency. And then those enhanced winds can result in enhanced motion over, say, a warm front, which means enhanced precipitation. For example, with northeast snowstorms in the United States, this has been proven that this isobaric forcing of the low-level jet by an enhanced upper-level jet can produce very intense snowstorms and blizzards. The resultant increase in diabatic heating further intensifies then the surface cyclone, and you get a positive feedback process. So this is not just about snowstorms in the United States. It's also true with tropical cyclogenesis. Although Coriolis and baroclinic effects may be insignificant, the process of PV generation by deep diabatic heating and the generation of inertia gravity waves are significant features, as well as Rossby waves. Rossby gravity waves are significant features in the subtropical and tropical environment as well. So that is it. I've got about 10 or 11 minutes to talk about convect and the North American monsoon. Dave, do you want me to just jump into that?
Yeah, go ahead. Yeah, we got time.
Okay. I'm watching my clock carefully here.
Yeah, I'm not. I'm just listening.
Okay. So I'm not going to say too much about the North American monsoon. I figure you all know about this anyway, but you may not know much about convect, which is a proposed project for which I'm a co-lead. I am the co-lead. So you all know that the monsoon is a worldwide phenomenon. We often think of the Asian monsoon or the Indian monsoon or the southeastern monsoon that affects China. And so on. But there's also the North American monsoon, and there are other monsoon areas in Africa and so forth. But I want to focus on the North American monsoon. By the way, before I leave this figure, the common thing about all these monsoon areas is a proximity to a warm tropical ocean and a significant orographic uplift. For example, in Mexico, the plateau, Sierra Madre Occidental, is the forcing mechanism. Clearly here with the Himalayan mountains and other mountains, the Ghats and so forth, a significant uplift occurs here as well. And also is true in East Africa and so on, and the Andes. It's the same story worldwide. In Western Mexico, you know that about 70% of the rainfall occurs in association with the North American monsoon. In Arizona, I live here, very close to the border. And we get about 55% of our rainfall from the monsoon. So hazards with the monsoon are abundant. Flooding in arroyos, canyons, dry riverbeds. Here's one near Tucson, close to where I live, Sabino Canyon. And this is a mudslide or debris flow. Last time I saw something like this, I lived in Boulder, Colorado, and it was a flash flood that occurred in the Rocky Mountains. And I saw boulders of this size. And I could not believe how this could happen. But it happened right here in Tucson. And it was associated with monsoon flooding. The arroyos are very nasty. They're bad, unpredictable things. Because where that water comes from could be 20 kilometers away from you, maybe over a storm over the mountains. And suddenly you see this water approaching you. Maybe some of you have experienced this in the desert. Very common here. I have to say I've experienced it more than I like to think about it. Microbursts are a second hazard, or dry microbursts. These are primarily danger in the early part of the monsoon season, and they promote wildfire spread. In fact, something like 65 to 70% of wildfires in the state of Arizona are associated with, yes, dry microbursts. That's a very big problem where we live. Wet microbursts, like you're seeing here in your Tucson, are more tropical-like, basically a moist adiabatic profile. They occur later in the monsoon. Dust storms, sometimes called haboobs, like here's one near Phoenix, associated with rapid movement of air associated with a dry microburst. I can say I've experienced this on more than one occasion as well, and it's impossible to drive through a dust storm like this. And they're typical as the hum monsoon gets going. So that's my little preview about the monsoon. So let's talk about convect. Some of you are probably familiar with a project called NAME, the North American Monsoon Experiment that occurred about 20 years ago. And the focus was in Mexico. Convect, the focus is in Arizona. But for the first time, it's going to capture the complete physical chain of land-atmosphere processes that drive water vapor transport and monsoonal precipitation over complex terrain at scales from meso-alpha to meso-beta to meso-gamma to even microscale. This is not what NAME was all about. This is clearly very different than that. We're looking at the diurnal cycle, which is including transport of moisture, momentum, energy over this heterogeneous surfaces such as canyons and up valleys, up mountainsides. These are thermally driven circulations in the planetary boundary layer, PBL. And then also looking at the venting of dry PBL air into the free troposphere before the first cloud forms. So again, this is different than NAME also. If you're starting with the initial growth of dry, thermally direct circulations that vent air up the mountain slopes before the first cloud forms. And then the questions we ask are, will a cloud form? How deep will it become? Where, when, and how rapidly will it grow upscale, and will it propagate off the mountains into the valleys? These are the questions that we are focusing on in a proposed program to the National Science Foundation called convection. This program is very large. NSF, National Science Foundation, characterizes it as a quote unquote complex program, which means it's a $10 to $15 million program. It involves multiple resources, aircraft, soundings, and all kinds of instruments, and many different institutions. So it's a very large program. So yeah, we'll have a network of surface flux measurements, energy balance, surface energy balance probes, thermodynamic kinematic profiling systems from ground and aircraft, crewed and uncrewed aircraft, mobile radars, fixed radars, you name it. Multi-scale modeling from large 80 simulation scales with grid lengths on the order of less than 100 meters, all the way up to the scale of numerical weather prediction on the meso-alpha scale. And as a part of the numerical weather prediction, we're interested in doing a simulation of the data, both in real time and after the end of the field phase. Just want to say one thing. Never before in an NSF project has there been real-time data simulation into a model to support the project decision-making on a day-by-day basis. We are indeed proposing to do that, where we would assimilate data and provide real-time forecasts with assimilated data to support the project. In a very general sense, there are three believed sources of moisture into central Arizona. Here's Phoenix, and here's Tucson. One of the primary sources believed to be from the Gulf of California, but I've lived here enough time to realize that moisture can come in from Sonora. And what I mean by that is thunderstorms. It's a very, very convective area. Here's Nogales. This is Sonora. This is a very convectively active region. And the storms produce rain, and then the moisture is advected northward into southern Arizona and even further beyond that. The third one is very controversial. This is called the Chiricahua Gap. And if you look at this and zoom in on this, here's Arizona, New Mexico, is West Texas, Mexico. So here's your Sierra Madre Occidental down here. There's a gap between the southern end of the Rocky Mountains and the Sierra Madre. This gap is about 4,000 feet above sea level. Air that comes up the Rio Grande River can actually cross through this gap westward, northwestward through valleys, and actually enter maybe as far north as north central Arizona. GPS-MET is a valuable instrument. These measurements of precipitable water are made every 5 minutes. Dave Adams is an expert, internationally recognized with his installation, use, and interpretation of these data. They are all weather, they're unattended, basically maintenance-free, but they do not measure the vertical profile moisture. Here's an example from an experiment called the GPS Transect experiment. Here's the Gulf of California. And I'm showing you three different cases. 1, 2, 3. And in each case, it all begins down to Los Mochis, right? And then you see in the water vapor here, this is Los Mochis right here. You see this happening first. You see the rise in precipitable water. And then later at Quino, that's the green. And then later at Puerto Peñasco. So this is 1, 2, 3. You see it moving northwestward up the Gulf of California towards southern Arizona. Here's another case of that. There's a third case of that. So this is a well-established behavior associated with the Gulf of California. And what causes this to occur are multiple sources. One is easterly waves or inverted troughs or the remnants of a tropical storm, and even sometimes baroclinic waves coming in from the Pacific Ocean area. So there's multiple ways to bring that moisture northward. In a modeling study that Bayu Rizanto did, he worked with Chris Castro. I'm a member of Chris's group with Dave and Bayu. He looked at what would happen if I assimilated GPS-MET data into the University of Arizona's high-resolution WRF model. And the bottom line is the top two panels represent with data assimilation, bottom two are without GPS data assimilation. And the bottom line is very simple. When you assimilate the GPS data, you increase the moisture here on the western slopes of the Sierra Madre Occidental. Here's the Gulf of California. You also increase the instability, and as a result, you get a deeper convective cloud with heavier, more intense precipitation than compared to the no data assimilation case. This is the good news. The bad news is the models tend to not do very well in predicting if and how storm and when storms would move off the higher terrain into the lowlands and develop into long-lived MCSs. This has not been modeled very well. Here's an example of Arizona with our UAF WRF model, and I'm running out of time right now. Real briefly, I'll just say this. Where are we? Here's Phoenix, here's Nogales, and Tucson. This black box is the area of focus for convect. It's focused near Prescott, Arizona. It goes up to Flagstaff. The colors here represent the probability of detection of daily predicted precipitation exceeding 10 millimeters from this model system. As verified against MRMS. This is a National Severe Storms Lab product. And this is for a 4-month period of time, 2021. The colors in red here represent very high probabilities of detection on the order of nearly 1.0. But look at the low-lying areas here, east, up here. And if you zoom in on this area, here's Prescott again. Here's Flagstaff, Sedona. You have the Bradshaw Mountains, a valley, Prescott Valley, Black Hills, Verde Valley. Go on the Verde Valley, we have the Mogollon Rim. And where do you get the highest probability of detection? You guessed it, over the mountains. Where it's bad, over the lowlands. So it's not just a problem over northern Mexico. It is a problem in Arizona, throughout the entire state, probably many other locations that models have this problem. So we're developing multi-scale radiuson and GPS met arrays. These circles represent soundings that are 3 hourly releases at all these locations. This is what we call the meso-alpha scale array here. And then embedded within that are 2 blue triangles, this one. These are meso-beta scale. And then embedded within that are these red triangles, 1, 2, 3, 4, 5, 6. These are meso-gamma scale. So the focus is on the area east of Prescott. But at each one of these locations where we're launching radiusons, we have continuous measurements from GPS MET. So we don't have the vertical profile information about moisture from GPS MET. We do it from the radiusons, and we have continuous time measurements, though, from GPS MET that we do not have with the radiusons. So we're looking at a blended product by joining the two kinds of data together in an optimal way. And as I zoom in on this area, here's Phoenix, here's Prescott, here's the 2 blue triangles, and there's an area, these are all GPS MET sensors, very tightly clustered here in the Prescott and Verde Valley areas. And if I zoom into that further, you can see that there's all kinds of other symbols here that represent all kinds of other instruments. And I don't expect you to read any of that. I have something I'll show you in the next page that discusses that a little bit more. But if I zoom in on this little box, this is a micronet, a micrometeorological array, a flux airshed with 9 3-meter flux towers and surface energy balance sensors that are looking at the mountain venting, the dry convection part. So this is my second to last slide. I don't want you to read all this. My gosh, don't do that. But basically we have soundings, including GPS MET, and many of them, 24 to maybe 30 of them. We have supplemental 3 hourly soundings, and we have other systems, as you can see from NCAR, integrated sounding systems. They have other instruments on them, like microwave wind profiler, Doppler wind LiDAR, aerosols, and so forth. We also have surface facilities. We have the surface flux systems, surface energy balance sensors. We're looking at anisotropic turbulence. We have mesonets, surface mesonets, and mobile mesonets. We have micropulse dial from looking at very detailed moisture profiles. and interferometric infrared temperature moisture measurements from ARRI. We have 2 aircraft, one from the Navy, Naval Postgraduate School, the Twin Otter. We'll have a Raman LiDAR for measuring moisture, temperature, airborne Doppler LiDAR, an isotope analyzer, which will be useful for determining the source of the water vapor, whether it's low level, high level, where did it come from? All kinds of things related to that question. Backscatter LiDAR and so forth. We have, I think there are 12 of these crewed Cessna aircraft that are training aircraft for the students at Embry-Riddle Aeronautical University. We'll be flying them, as well as VTOL, vertically takeoff and landing UAS. We have 5 radars, 4 C-band, 1 X-band, and these mobile systems, including a very interesting system called PASSIVE, which is a hydrometeor probe balloon system, which does very detailed photographic imagery of hydrometeor types, changes, particles, and density distributions. Many other things. So the science is 3 parts. One is on surface fluxes, quantifying the fluxes, not just one-dimensional. Those of you who've studied surface and boundary layer understand Money-Novikov similarity theory as the underpinning for boundary layer parameterization and surface layer parameterization schemes. Here we're looking at anisotropic turbulence that has a horizontal component to it as well. Secondly is convective boundary layer growth and the venting of the moisture up the mountain slopes as the boundary layer develops during the late morning. And then under what conditions mountain venting generates deep moist convection. The second objective has to do with what happens to deep moist convection once it's generated. Under what conditions does it move off the terrain? Under what scenarios? And under what conditions does it grow upscale into long-lasting MCSs or MCCs? And finally, the modeling and data simulation, we're looking at coupling these large 80 simulation models or microscale models to mesoscale models to improve the parameterization of subgrid scale fluxes, including turbulence and isotropic and dispersive fluxes. And then real-time and after-the-fact numerical weather prediction and data simulation. Using what's called data denial studies, we can look at the impact of individual observing systems on predictability. And using ensemble sensitivity experiments, we can conduct other kinds of experiments looking at the role of physical parameterizations, for example. And a lot of interesting questions for the modeling. I won't spend any more time, and I've run out of time. And I think I ran over by 5 minutes. I apologize. But that's all I was going to show, unless someone wants to talk about NSSL. But again, thank you very much. I'll go back to my thank you slide and take it from there.
All right. Thank you, Steve. That was great. You definitely demonstrated your vast amount of knowledge with everything convection. Bueno, quiero abrirlo a preguntas. Déjame ver. Pues no entiendo si va a ser por chat o sea escrito todo o así si se puede pues preguntar. Y si no, pues quieren decirlo en español, yo lo traduzco o hasta escrito y si no en inglés, ¿no? Okay. ¿Está bien así, Erika, o quién es mi coordinador?
Yo te ayudo. Aquí estoy, ¿me escuchas? Sorry.
Ok, sí.
Sí, está bien, como dijiste tú, que cada quien pregunte en español o en inglés como se sienta cómodo y en el caso de que sea en español, tú nos ayudas a traducir.
Ok, sí. Okay. Bueno, yo hago una pregunta. Okay, yeah, Steve, actually, I think we talked a little bit about this the other day in what you call mixing or what you call transport from Sonora. Yeah, I agree with that, and I think that's very important. And I actually think that's where Ralph and Galarno get confused, or they get I don't know what the right word in English or in Spanish is, but I think they mix things that shouldn't be. And I would argue that it's certainly important, but also the Gulf of California is the source of and Eastern Pacific is the source for the Sierra Madre. in that respect. I mean, you're right. It might not be the Gulf surge type episode, which is very unique. But ultimately, if you look at, think with the name, you look at the diurnal circulation of, upslope flow, the convection initiates over the highest peaks and then under certain conditions will propagate down towards the Gulf of California. But regardless, I would say that's Gulf of California moisture to a great deal, no? And I don't think it's Gulf of Mexico or anything like that. And I know there's fights and arguments over this. Would you agree with that statement, or?
Yeah, but I guess I'm not going to presume I know that the answer is that. I personally think that the Sonoran moisture source is very important. I'd underemphasize. The question about the Rio Grande River and coming up to, well, you know how it is. It goes on up to Albuquerque and so forth. So it veers off to the north. But having driven through the Chiricahua Gap before, it definitely can allow for some moisture to come up through the area that actually occurs before any storms have developed in Sonora. And I've seen this year on several occasions, thinking it looks to me like the source is actually coming in from West Texas and southern New Mexico. But so I'm not going to prejudge it. I'm going to say I understand what you're saying, why you believe the Gulf of California is preeminent. And I do agree with that. But whether Chiricahua Gap is important or whether it should be reinterpreted as Sonoran moisture or even Chihuahua moisture, I'm not going to say at this point.
Okay. All right. Let's see. Do we have any other questions? I can't see. Oh, okay. Jorge, did you have a question? Or modeling, los de modelación? I'm trying to provoke Steve.
I see that.
Okay. Bueno, entonces, vamos, pues si alguien quisiera hablar un poco más de la cuestión de, pues, su tiempo en NOAA's National Severe Storms Lab, él también puede estar dispuesto a hablar. Y bueno, la idea es que espero que podamos conseguir, bueno, si este proyecto de Convect, pues nos dan el dinero, entonces pues vamos a buscar algo en México, conocido o en otro, para poder, pues, que nosotros podamos traer equipo, pues, postdocs, alumnos, investigadores, ¿no? Pues sería loco perderlo, ¿no? Entonces, bueno, pues cualquier duda o pregunta después me pueden preguntar y se lo mando a él. Okay.
Mm-hmm.
All right. Anything else, Jorge? Jorge, algo?
Well, I think it's very interesting to see what is going on, and there are 2 or 3 groups that have been working on the surface fluxes in particular, and a lot of interest in particular on latent heat and other surface fluxes, but certainly mainly on the Mexico City area. But the idea to have better models to reproduce these surface to atmosphere models and how these evolve could be very also helpful, because it's in the same direction, I guess. And I wonder that this kind of process, what the scale that you can expect for this development of these feedbacks, probably.
One thing I'd like to say about that, I didn't mention this, but there's going to be a lot of emphasis in Convect on land surface atmosphere interactions. What specifically I mean by that is we have experts on the team in satellite remote sensing, and then me. I don't consider myself an expert, but I can speak to them. And the emphasis is on shallow soil moisture, deep soil moisture, and transpiring vegetation, or what we call green leaf index. And all 3 give rise to evapotranspiration. People argue with me on the team. They say, well, why can that be important in Arizona? It's a very dry climate. And I say, well, if you ever have gone up a mountain, you realize there's like 5 ecoclimate systems as you go up the mountain. Okay. It may start at the bottom as a desert, but at the top you have ponderosa pine forest. And I do know that the trees will evaporate a lot of moisture. If there has been rainfall recently in areas, it's very interesting here in southern Arizona. We have countless numbers of what they call sky islands. These are these limited ranges of mountains, not very long, maybe 50 to 75 kilometers in length, but there's many of them, and some of them do have this kind of vegetation at the tops of the mountains that could act as a moisture source as well. So there's going to be emphasis on land surface heterogeneity in terms of that interaction. The difficult thing is with deep soil moisture, it's almost impossible to know how much moisture is in the root zone of the vegetation. There's nothing from microwave or infrared satellite imagery that speaks to that directly. At the most, maybe 3 to 6 centimeters down into the soil is all you see. And so there are other ways to get around that problem, but they're more indirect. Anyways, I just wanted to emphasize land surface processes.
Okay. Do we have any other comments, questions? Okay. All right, Steve. Bueno, pues thank you very much for this very interesting talk. I assume it will be available on YouTube, or several people told me they couldn't come today or attend, whatever the word would be, and they'd like to see it later. So this will be, I think, on YouTube or the normal places where we send it, right, Jorge?
Yes, right.
Okay.
You know what I could do? I made a couple of changes in the last day or two, Dave. I'll put it on the Google Drive, and then you can download it, and then you can put it on YouTube or whatever you want to do. Whatever you want to do is fine.
Okay, no, but I mean, your voice in this session with the questions and my voice and everything would be actually on YouTube or Facebook or whatever the.
Yeah, both. It will be in both.
Okay. On
Okay.
both.
I understand.
So that's why, yeah, it's good. Yeah, but you got to be careful with what you say.
No.
Yeah.
Okay, bueno, pues gracias, gracias pues al instituto por pues haber invitado a Steve, y sí, espero que este proyecto sí se dé, ¿no? Y pues ya veremos, ¿no? Y eso sería para el 2025, no es este verano que viene.
Muy bien.
Es un experimento de como 6 semanas, algo así.
Okay.
Okay.
Well, it's been my pleasure. Thank you for inviting me. Seriously, I very much am honored to be able to speak today.
Okay, gracias, Marvin. Okay, perfecto.
Okay.
Does anyone want to hear about NSSL, or do you want to?
From what I'm gathering, Steve, no, it doesn't look like it. I'm actually surprised. I thought people would be very interested in that, but
Okay.
yeah, I think people are probably. It looks like they're abandoning now.
Yes.
Okay. Bueno. All right, Steve. So we'll keep in touch and moving forward on this. When do we actually have to submit the proposal?
20th of December.
Oh, okay. So we still got a little bit of time. Okay. Okay. Good. Okay. Bueno. All right. Thanks, Jorge. Thanks, everybody.
Saludos.
Okay.